relate the rotation and the relative velocity. And for the Earth, it's 10 to minus 8 or something like that. So quite 10 to minus 6 more precisely. Sorry, I don't remember exact figure, but something like that. So, which is so small that the original equation are linearized. So actually we remove this Rossby number. And we are left only with one parameter. In this case, the entire system rotates so quickly that the only remaining similarity criteria, the Ekman number, can be considered asymptotically small. So actually all the game is around this Ekman number, and we get in different boundary and shear layer which is dependent on this boundary. As a result, outside the tangent cylinder, which is shown on this figure as well, outside the tangent cylinder, the fluid is in solid state rotation. It was a special figure where we discussed that the outside the tangent cylinder, in terms of the just trophical flow, the fluid is in the rigid rotation, but inside there is some just trophic flow. Very simple, monotonic one. That if we consider angular rotational rate, it just monotonically rise from the beginning, from the center of the near the axis of rotation. It's about 1/2. Then it rising up to unity, and on the boundary between on this boundary, it has dramatically higher, even infinite derivatives, and here it's just rotates rigidly with the mantle. And I just remind you that here we have a mantle if we consider this picture in the terms of our native Earth. And its profile determines the balance of the amount of fluid flowing in and out of the outer and inner Ekman layer at the same distance from the rotation axis, and thus the meridional flow in the tangent cylinder is concentrated in narrow Ekman layer, and in the main volume of the tangent cylinder there is only a weak e to the 1/2 axial flow directed from the outer Ekman layer to the inner layer. So there is some general flow, and there is only small contribution from this part where the shear layer and boundary layer are intersected. And here also there is such a structure where we even have special equatorial type shear and boundary layer combined. The return flow of the liquid occurs on a complex shear and equatorial Stewardson layer on the tangent cylinder. So there is a upgoing flow inside the tangent cylinder, and there is a return flow. And all this return flow is important because actually it's working in the shear layer. So we discussed this shear layer. It's very important in the terms that it's produce the return flow, and it has very small scales. So if we consider, for example, for future application of all this picture to the magnetic generation in the planet, we see that the most important gradient are directly on the tangent cylinder. And so we can make the simplified model which catch this feature. And frankly speaking, almost nobody. People just find when they are making their model of the geodynama and planetary dynama and so on, and solar dynama, star dynama, whatever. They of course notice that there is very crucial role of this tangent cylinder, all the shift layers. Stewardson, typical, of course they are not exactly Proudman Stewardson, but very similar. So why to, for example, I'm just saying the idea, why not to investigate this case when we have applying the special numerical procedure just to resolve this layer. So we just have more point here and less point here. And so again here with the more point and less here. So, and of course, near the boundary should be more concentrated mesh. So actually, we numerically could take into account all these features, and so eventually we obtain the flow. So here the sharp discontinuities as angular velocity of rotation are smoothed out, which reach the maximum value on the tangent cylinder and immediately outside the tangent cylinder. And immediately outside the tangent cylinder, it turns to the zero. In addition, the weak meridional current, which also has sharp discontinuities on tangent cylinder, is smoothed out here. Each of the layers is responsible for smoothing out individual characteristic of the flow. The Oh, I jumped. Sorry, I jumped. Okay. Okay, sorry, I jumped. Oh. Here the sharp discontinuities and is smoothed out. Here, each of the layers is responsible for smoothing out individual characteristic of the flow. And the most important layer is one with thickness e to the 1/3, since the second derivatives of the angular velocity of rotation, which is directly related to the energy characteristic of the flow, is smoothed out, and actually you can see the problem which is stating this cause for you. And the structure of the boundary shear and equatorial layer becomes clear already at Ekman number about 10 to minus 3. It is especially clear manifested through the lines of constant angular velocity, which are shown in the following figure. This following figure, this one, was the direct numerical calculation, the same situation. And you see that even for the Ekman number 10 to minus 3, not that small, like in the where it's 10 to minus 8 or 10 to minus 15, we already have all the structure which we just discussed it with you. And this, all the structure appears here. So you see that there is Stewardson layer which is appear here. It's the actually for angular velocity picture. And here there is almost rigid body rotation. Of course, there are Ekman layer. Here there is the Ekman layer. There is another Ekman layer. There is a tricky equatorial Ekman layer which appears here. Of course, if we proceed further, we have a more clear picture for all these things, and eventually we can outline. But it's nevertheless, if we proceed slightly further, even to 10 to minus 5, this actually will be so thin that it's impossible to see. But of course, we can make this some magnification of some places, and so it could be interesting work to at least illustrate how all these things are working. And also, this work could help us to formulate the idea how to do it more properly, everything of that. Okay, so actually we almost finished this part of my lecture course, which is related to some sort of the general hydrodynamics in application to the planetary situation. And on the next lecture, which will be tomorrow, we will start already with convection. So we will all this stuff which is related to the general hydrodynamic is stopped here actually. So, but only because this the last paragraph is the most complicated one. So I can give you sort of the complementary task. If you solve them, then you are a perfect person. And then if you don't solve, no any obligation, you can pass the ordinary exam. And so I don't know, Maria, will be this task available or?
Before that or after the exam, but during the day. I'm talking about first 6 tasks. And with extras, of course, it will be given and discussed later. So, yeah, what I meant that you now have the possibility to ask specific questions on these tasks, on these first 6 tasks, if you got any. Because today, we're supposed to submit them. Yeah, let's do it like this. To ask those questions about first 6 tasks and extra tasks.
Okay, but
the discussion of extra tasks is planned for tomorrow. Yeah, some special.
no, you mean extra task which is this chapter,
Yeah.
which related to this shear layer. But I think that this is sort of premium task.
Yeah.
So maybe we could consider this is quite difficult subject. So maybe we will consider the premium task. The previous task, like just all this.
Yeah, there's tomorrow we've got a special report of 6 special
I thought that tomorrow was
No, the lecture and tutorial.
So tomorrow, as Maria told you, you can ask me what about this extra task, and if you answer this extra task, you will be premium student or something like that. And as well as I'm able. By the way, I didn't say that. Just let me do some comments. Some comments on the Proudman-Stewardson.
Because actually to answer this task, this Proudman-Stewardson paper is very important because everything is there. You see that even our combination of the all the spherical shells is. This paper is accessible. Maria, is this paper accessible for the student? Proudman-Stewardson. Okay, so you can easily take this original paper. Everything what we are spoken about is everywhere here, but much more, even much more. So important things to know that here he used not Ekman number, but the inverse Ekman number. So this R is in fact inverse Ekman number. So now it's become not small but larger parameter. But this larger parameter is you have higher order derivatives, which is the second order, and you divide by this larger parameter. So effectively, you have small parameter near higher order derivative. And if we consider how this working, you see there is a statement of the problem. Then he wrote the different notation. Some of the notation are exactly as ours. Omega, for example, he also used. And there is also, of course, quite different rotation. He used for cylindrical radius, he used rho. And for z direction, he used this variable. So there is some difference in notation, but it's not so big. And of course, he operated slightly different manner than we did. He used the flow functions, and so he reduced to just one function, which is written here, or two, and then he manipulates this equation as in a similar way as we did. But there are some difference. For example, he accounts boundary condition like that, not exactly like we. And then he solved this system. Reduce the system to the simplest layer, then consider the boundary layer, Ekman boundary layer as we did. And actually, only the up to notation, it's quite similar what we did. Maybe you remember there is a fourth derivative in the stretched variable. Here there is a second derivative in the stretched variable again. And this cosine is the composition Coriolis first term, which is actually neglected here. Not neglected, sorry, so it was used here, so it's quite similar stuff. So then there is also different representation of the function, and he got the solution for this boundary layer near Ekman boundary layer, which is exactly like ours. Of course, there are some difference in notation, but in fact it's the same. And then, he found that there is a solid body rotation. This means in his notation that there is solid body rotation outside the tangent cylinder, and there is a boundary layer condition that there is imposed. He used just two functions, not three as we used. And then he proceeded further. Then he stated the Stewardson layer, how it's work. And for different combination, he started from the equatorial layer, with which we finished, but he started with the equatorial boundary layer, and also wrote the similar equation and prove them in some manner. And then he proceeds even further, and he proceeds to this 1/4, 1/4 and 1/2 boundary layer. Here he got the solution. Okay, see, you see, and this is after the considering this Ekman type boundary shear layer, because it's a boundary and shear simultaneously. He proceeds to another floor, another shear layer. In our term, this is the most important shear layer, which is in our notation e to the 1/3. And here he made the manipulation and managed to find the solution to this problem. Rather simple solution, which is shown here. But then it's complicated, and it even find this value of the flow, which is made full adjustment. I did one Ekman number in 128. It's quite tricky, but nevertheless, from the rigorous asymptotic analysis, it's coming out. So there's additional difficulty which I didn't load you. And also, but if you like, you can understand how it works. And there is also the inner layer. In our notation, we call it innermost boundary layer. And here he made some expansion, again got the precise asymptotic solution. And then he proceed further, as we did. Maybe you remember that we were taking the integral just to have the acceleration for the function. See, he is doing similar things. And proceed further, but there is some things that we didn't do, because maybe they are in terms of the value not so important, but in terms to match all the asymptotic together, of course they are important, and there are quite tricky stuff like this 112, 112, 21 power, very complicated. And so eventually he found almost exact solution for all part of this problem. You can just see them and understand. And this is quite interesting stuff. And again, I should mention that in fact all this stuff is at that time it was 1966. At that time it was no computer technique. And all this nice, all this beautiful stuff which Stevenson found, you see that he found everything, all the function, all the matches, all everything. So he expressed all the which available in a very detailed and actually in asymptotic semi-algebraic form. So it's a big advance. It could be maybe quite interesting to repeat it on the computer and to compare this asymptotic solution and computer solution. So maybe if you succeed to understand this article, you could regard you as a true scientist. So my suggestion is just to go through, because actually there are plenty of ideas how to work in different difficult situations, shear, boundary layer, and of course eventually with the turbulent stuff and so on, which is perhaps it's one of the most advanced work till now time. So in this ancient time, people were quite clever. Okay, so maybe there is no, it's okay. There is, you see that not so big reference list. People at that time made very original things and very clear stuff. Okay, so maybe there is some question to all this heavily interested part. But anyhow, you can think a bit, and maybe tomorrow when you, Maria, excuse me, will be this task available on the net that they should understand what to ask? Yeah. Okay, everything will be available to you. You just see, and you find some question for me, you please welcome tomorrow, and you say that. And tomorrow, hopefully, we will proceed further to the convection. Maybe it's more realistic stuff. This, of course, some sort of the. Of course, it's classical problem, very classical problem, very deeply founded, and it's very fun of the science. But nevertheless, it's not so practical. But it's an interesting situation that very often not so practical problem solution becomes very strongly available. So we hope so. So one day this Stewart's and law will will be available and help us to understand the very essence of the science, because it's rather tricky stuff and complicated and interesting from my point of view. Frankly speaking, even some places I didn't understand. Okay, maybe if there is no question, then it's one. Okay, so we finish, yeah. Okay, thank you for your attention. Yeah, you can prepare the task. The question about this task you can ask me. And perhaps if you perform this extra task, at least just some of them not so difficult, but it will manifest that you understand. Okay, we can stop.